So I think the morning went really well, and I enjoyed my lunch. So I hope you did too. So we have three speakers this afternoon. First, we're going to start with Nick Kovachi, who comes from NVIDIA, and he's going to talk about operator learning. So let's welcome Nick to the stage.
Okay. Okay. Can you guys hear me?
Yep.
Okay. Yeah, thank you so much. Thank you so much for John for inviting me and Thorsten also for organizing this great conference. The morning has been really nice. So today I'm going to tell you basically a little bit about operator learning. So John mentioned this morning a whole bunch of different kind of neural architectures that's been used to try and solve physical problems lately. And one of the things he had on his slide was neural operators. So hopefully I'll try and take a little bit of a deeper dive into what that means and kind of the dogma of designing approximation architectures in this particular way. So the title is From Theory to Practice. I think due to time constraints, it's mostly going to be theory, but I will hopefully show you at least one a little bit more serious engineering example where this actually does work in practice. Okay? Okay, so we can get started. And I don't, okay. Okay, so basically I'm going to start with just telling you a little bit about the kind of problems that I'm going to try and think about and the kind of problems I want to solve. And then the kind of architectures that I'm going to design. And then really I'm going to get into the particulars of these architectures, and I'll talk mostly a lot about approximation theory of these architectures, one through what's what I'll call parametric complexity. So if I want to get a particular error, how many parameters do I need? And also data complexity. So how much data do I need to achieve the certain error that I'm looking for? Okay? And then hopefully maybe I'll get into some engineering applications depending on how time goes. Okay, so let's start with the kinds of problems that I want to solve. So generally, I'm interested in kind of larger scale engineering tasks. So one can be like fluid simulations in very complex domains, where say you have some car and you want to say figure out if this car is moving, what is the pressure field on the car, or what does the velocity stream around this car look like. Or let's say you want to design some kind of material, I care about, if I have some impact with this material, how would this material deform? Or in a situation where maybe I don't know all the physics, like the weather, I would want to be interested in predicting, say, the dynamics of this large-scale system, which is the weather here. Okay, so these kinds of problems I like to split in sort of two main categories that I can think of. In the first two are ones where I generally don't tend to have a lot of data, but what I do know is maybe I can model the physics really well. And the other one, like the weather, is one where I do have tons and tons of observational data, but I don't necessarily know the physics of all the multi-scale interactions. Okay? The methods I'm going to talk about today are generic and will work for any of these problems, but I would say that sort of as future work and where this field should head towards is being more specific and taking into account how much data or how much physics you actually know about a problem and really building that into the kind of things you design. Okay? But for the purpose of the talk today, I really will talk about generic methods that should work for all of these. And hopefully at the end, I'll show you examples of these. Okay, so the goal is really to design architectures which will speed up these kinds of simulations or will in some way learn about the physics that we don't necessarily know about within these systems. Okay? So let's make this specific. So I'm going to just first set up some notation and give you the general dogma of how I like to design architectures. So I'm going to assume that there's going to exist a map, which I'll call GDagger, and that this is a map between infinite dimensional spaces. So spaces, all spaces I'm going to care about in this talk are going to be spaces of functions, which I'll assume they will be infinite dimensional. And I will essentially never discretize until I actually have to get a method that I can implement on a computer, okay? So I'm going to always think and always design architectures with the point of view in mind that everything is a function, okay? So, and in particular, what I'll take is I'll assume to have data. So here pairs A and U, which are going to be either going to come from, so my inputs A are either going to come from IID, from some measure mu, which is supported on X, or they're going to come from some compact set K, which is, I kind of have a predefined idea of what this compact set K looks like on the space X. And then my U's are simply going to be the push forwards of my inputs through the data. Okay, so very standard kind of supervised learning approach. But with the caveat that I'm thinking of everything not being discretized. So I'm thinking of the objects A and U really as the functions, the infinite dimensional objects, and not any discretizations of them, okay? And so then my goal will be to how do I take these functions, and how do I design mappings, so parametric mappings, which are going to be finite dimensionally parametrized, so with parameters living in Rn, which can take functions and output functions, with the goal of approximating my operator G dagger given this data, okay? And for the purposes of kind of a theory, I'll look at two metrics. One will be an average LP error over the measure mu, if my data does come ID from mu, or I'll look at kind of a worst case error across the set K, okay? So these will be the way I measure error for everything I do. And just kind of so the following is just an example to keep in mind, as in what I'm trying to do. This is not an engineering problem of any kind. This is a relatively simple problem that we know how to solve quickly and don't need these kinds of architectures for. But it's I think it's a prototypical example that you should just keep in mind whenever I go through these architectures. So I have this second-order elliptic equation with diffusion coefficients A and forcing F. I'm assuming the F is held fixed, and the boundary condition here is just 0 Dirichlet, so that's held fixed. And what I'm changing is the A's, which are the diffusion coefficients, and I'm trying to map the A's to the solutions U. Okay? And that's a nonlinear map. So even though this is a linear PDE, this is a nonlinear map from the diffusion coefficients to the solution U itself. And the spaces involved here, since I'm working with separable spaces, I'm looking at some subset of L infinity, where my A's live, some separable subset of L infinity, and then my solutions U live in the Sobolev space H1. Okay? So in computer vision, this is kind of called an image-to-image problem. But the idea is that I'll never think about these as being discretized. So I always think about these as the pure function in kind of infinite resolution. Why is that kind of important? It's because then we can decouple the parameters of the architectures that we build from any particulars of the discretizations of these functions. Okay? So a really nice example that I like to give of what this looks like is through the heat equation. And why is this useful kind of in practice? So if you just look at the heat equation and then you semi-discretize it, I can do that here in two very simple ways. One, if I do a forward Euler discretization, and the other one is if I do a backward Euler discretization. Okay? So if I kind of follow the forward Euler case, then what I get is an iteration that has in it an unbounded operator, right? It has the Laplacian in it, which when you apply, is unbounded in the function space, and this iteration makes absolutely no sense in the function space. Like, without me spatially having discretized the U's, this iteration makes absolutely no sense, because at every single point of this iteration, I lose two orders of regularity, right? And so what that means is that when I do, in fact, discretize, I have to relate the way that I discretize to the step H that I take, right? So this is the CFL condition, and it just tells me that I need to take smaller and smaller time steps, the finer and finer I discretize. On the other hand, if I go to the other side of this page and I look at the backward Euler equation, now that is a perfectly sensible recursion in function space without having discretized, because I'm applying a compact operator every single time, right? And what this tells me that my time step H now that I need to take no longer has to depend on how I discretize, okay? So I want to take this idea and apply it here now to designing machine learning architectures, okay? With the simple idea being that if I can design some approximation architectures of this form, and I don't tie any of their parameters to the particulars of how I discretize my actual system, then what I should get are architectures that work exactly the same for any kind of discretization of the system, okay? So this is just the top panel here is just intuition for how I want to actually design approximation architectures, okay? And just before I get into the details of these architectures, I just want to give you an example that this does work in practice. So this is a thing that actually, if you do this kind of correctly, you will get something that actually works and does this. So here, we've taken like a standard UNet, which I would say is not discretization invariant, and I can tell you why that is later. And then one particular very simple instantiation of this idea that I've just given you. And we've taken the same exact data at different resolutions, and then retrained these models at each of these resolutions that we have the data at, and we've measured the test error there, yeah? And what you can see is that, yes, so the UNet basically gets worse and worse and worse the more you refine, even though you plug in the exact same data, but it's finer and finer discretizations. Yeah? While with this other architecture, you don't get that. So this essentially decouples your parametric dependence from the discretization of the system, which is very useful because it means that you can have models with a fixed number of parameters work kind of at arbitrarily large resolutions, right? And you don't generally want to scale your models with the resolutions because then things can, computationally, they can just become unbounded and you won't be able to do anything anymore, okay? And so kind of a hope also of this is that when you train at one resolution or maybe some range of resolutions, you pick up how the scale of the physics changes, and then what you can do is actually transfer parameters between resolution without having ever seen data at these resolutions. Of course, this is just a hope. This is not something you can ever actually guarantee, but at least it gives you, it gives you the hope that you can do it. And we will see in some examples that is indeed the case. Okay, so that's kind of the dogma of this talk. I'll now try and get into particulars and details about it. A lot of this is going to be about the approximation theory, so I'll talk a lot about the curse of dimensionality and how that manifests into different kinds of architectures. And I'll start with the simplest kind of architectures, in fact, the one I just showed you right now, which is an architecture just based on model order reduction. So ideas like this have been used for the last 60, 70 years in model order reduction, where you just take the data that you have, you project it down to a lower dimensional space in a linear way, and then you try to come back out, okay? So let me just formalize what this means here. I have, again, my spaces x and y, and my operator g dagger, which I'm mapping, and then I'll define a pair of linear mappings. So these are going to be linear mapping from the function space x into some number of parameters m, which will take my functional data and map it into a vector in Rm. And then I'll take, on the other side, I'll take a decoder, d, which takes some vector of length n, and then maps it back out into a function space, again, in a linear way. And between them, I'm just going to link them with some kind of function phi, which is now purely a function between finite dimensional vector spaces, right? And here I'm going to use a neural network. It doesn't have to be a neural network. So the theory will go through for kind of any nonlinear function approximator that you like to use. But for what I'll care about, I'll just focus on the neural network case, okay? So what we want to do is basically find ED and phi so that this commutes through data, or approximately commutes through data, yeah? Okay, so maybe the first thing you can try and ask about this is, can you approximate anything, right? And the answer is yes. In general, you can approximate anything, and so this is just, you can just look at the top panel, ignoring the bottom panel for now. So this says that as long as you have a continuous mapping G dagger that you want to approximate, for any separable Banach spaces, you can approximate as low as you like, so you can always find an encoder, a decoder, and a nonlinear map, so that you can approximate as closely as you can, okay? This doesn't tell you anything about the structure of what these mappings should be, right? So all I've told you is that there exists a linear E, a linear D, and a nonlinear phi, which is continuous, so you can approximate as well as you like. And then the bottom panel says that you can also do this on average if you like, okay? Okay, so let me maybe now give you an instantiation of something that you can actually put in practice of this. So one idea that people have used many times is that of doing PCA. Okay, so you can now I can focus on the kind of Hilbert space setting because inner products are well defined, and I can do PCA. So in the case where x and y are Hilbert spaces, I can essentially take my data. So mu is the measure from which my data comes from. I can empirically compute what the covariance of that measure looks like. And I can also empirically compute what the covariance of the push forward of G dagger under mu looks like, because I also have data for that measure, right? So my pairs A define data for the measure mu, while my pairs U define data for the measure G dagger pushing forward mu, right? So now I can empirically compute those covariances, and from that I can compute the eigenfunctions of those covariances. And the moment I have eigenfunctions, I can now define precise encoders and decoders, right? So the encoder will simply be a projection onto the first, say here, m eigenfunctions, while the decoder just takes any vector in our n and expands it out into a series onto the eigenvectors of the push forward covariance, okay? And there's been, so this is just one particular idea that comes from model order reduction. Many people have done this. Another idea you can use, for example, is something like DeepONet, where you can, instead of empirically computing these things through a covariance, you can extend, plug them, you can parameterize them by neural networks or by something else and try to directly learn those parameters, okay? But in this particular case, you can actually do an analysis on this, and you can do a full analysis. Particularly, I can get both a lower and an upper bound on the error of this. So let's focus first on the upper bound. So the upper bound says that if the sequence of alphas are the covariances of the eigenvalues of the covariance of my input, and the sequence of betas are the eigenvalues of the covariance of my output data, then on average, out of using n data points A, the error between the approximate architecture I just showed you and the truth is bounded by some neural network error, which I'm hiding for now. So this is finite dimensional error. So this is error that has to do with how well does the neural network approximate between Rn and Rm, that particular function, followed by some Monte Carlo error. So that's 1 over the root of capital N, which is the amount of data I have used to compute my covariances, plus the tail end of the two eigenvalue sequences of the covariance. So this is how fast do the covariances decay. So the faster the covariances decay, the less error I'll get. Okay? So this is essentially a characteristic of the smoothness of the kind of functions I have as input and the kind of functions I have as output. Okay? And what you can also prove is the lower bound of the same quantity. And the lower bound turns out to just be the eigenvalues, the tail end of the eigenvalue sequence of the output functions. Okay? So I've hidden kind of the neural network term here, but what this essentially tells you is that you immediately run into a curse of dimensionality if you use this kind of network. Because this sequence, which characterizes smoothness of the operator, if you take, so let's say smoothness is something like this being on the order of n to, say, the minus s. So if I can take s derivatives, then this would be like n to the minus s, roughly. Then this, so even if G is smoothing, this tells me that the output space is so large that I'll still need an exponential number of parameters in my neural network in order to approximate well. Okay? And if the only thing, so even if this is smoothing, I still need an exponential number of parameters. And if this is only continuous, then I get a logarithmic lower bound, which translates to an exponential upper bound in the number of doubly exponential upper bound. So I need doubly exponential number of parameters to approximate well with this kind of architecture if all I know about G-dagger is that it is continuous. Okay? So this is kind of the first instance of the curse of dimensionality that we run into with this kind of neural network approximation architecture. And the reason that this is exponential and doubly exponential is because this is a linear method of approximation. So a linear method of approximation means that the decoder D is a linear map. So the subspace of possible outputs from the decoder is a linear subspace, okay? And is not a nonlinear manifold. So there is some potential, maybe hope, of fixing this, okay? And that essentially brings me to the next part of this, which will be, if I want to be nonlinear, what can I do? And I'll give you just maybe a simple idea of how I can do this. In finite dimensions, neural networks are nonlinear approximators. So can we live this idea to the infinite dimensional spaces? Or can we design somehow architectures that mimic the neural network structure, but are nonlinear approximators? Okay, so I mean the answer is yes. At least I've done it for one instance here. And this instance is to basically design very simple operators, which you then just compose with one another to get a full architecture. Okay, so these here I'm calling S. Okay, so X and Y are going to be function spaces over a domain omega. So, and I'm going to construct my function class G to just be L compositions of such simple operators, each of which will have their own parameters. Okay, and each S will have the following composition, which precisely mimics what a neural network looks like, but in infinite dimensions. So a neural network in finite dimensions takes an input vector, applies a linear operation, right, multiplies by a matrix, then adds a bias vector, right? So it's an affine transformation followed by a pointwise nonlinearity. Okay? So you can precisely mimic this structure in infinite dimensions by simply saying that you're going to take some kind of compact, say, operator, a linear operator, and here I've chosen a kernel linear operator. And it will turn out, I'll show you in a bit, that having a kernel integral operator is enough, at least for universal approximation. Okay? So this part here is the matrix multiplication part of the neural network, and this part here, I guess, would be, well, here you can think of this kind of as the bias part, although it's just a pointwise linear part. That there is more, I guess, if you're familiar with residual networks, that part is more to kind of have better gradients in the computation of your parameters than anything else. So W is simply a pointwise linear operator that acts on your function A, and then the non-local part is this kernel integral E, and then the nonlinear part is only locally nonlinear, and it's pointwise. Okay, so you can define this on LP spaces as the nonlinear parts being the Minsky operators, then the non-local parts being kernel integral operators, and then the residual parts just being pointwise linear operators. Okay, so again, you can ask the same exact question. If I define something like this, can I get universal approximation? And again, the answer is yes. So this is a very ugly slide. But basically, it says that for a whole lot of function spaces that I might care about, say if I want to approximate PDEs, I can find architectures like this, which are universal approximators. So here, X can be any Lebesgue space, or any Sobolev space, or any space of continuous functions, and Y can be the same, so you can pick and choose any pair of these that you like. And if your G-dagger maps between them, then you are going to be able to find some kernels. So you're going to be able to find functions KL of this kind, as well as matrices WL of this kind, where the sigma L remains fixed, such that you get epsilon error. Okay? Now, okay, so now I've kind of said nothing about how you actually, like, what is a practical way of doing this, right? Because all this tells you is that I can find the kernel function, and I can find the matrix W, for which this is true. But in practice, you have to give some structure to what this kernel matrix will actually look like, or what would this, well, the W is fixed, but really, what would the kernel look like? And it turns out that you can do all kinds of things, and this will remain true. So for anything I show you coming forward, theorems of this type continue to hold. Okay? In particular, so the kind of layer structure that I'm looking at is going to be at the top. And the question I'm asking is, how do I parameterize kappa L? Okay, what are a good finite dimensional representation of kappa L? And people have done a whole lot of different things in practice. I would say that the most kind of efficient one, which has worked well on a lot of problems, is if you take kappa L to be one translation invariant, and then you parameterize with a spectral expansion. Okay, so instead of saying that, so basically this turns into a convolution, and I parameterize kappa L as just the spectral coefficients on some kind of expansion. So this can be Fourier modes, this can be wavelets, this can be kind of whatever your favorite basis is, and whatever one you think that works inductively kind of works best for the problem that you're looking at. You can take that, and then if for that particular basis expansions you have a fast transform method, in particular, if I can compute an expansion TA of my input quickly, then the layer on top simply becomes a pointwise multiplication just out of the convolution theorem and an inversion back. Okay, so in the case of Fourier, this becomes quite efficient because if I discretize omega into m points, then this computation is n log n, while normally this computation is n squared if I just try to directly discretize the integral in physical space, right? Another method, another kind of way that people have thought about making this more efficient is with directly working in physical space instead, but giving structure to the kernel kappa. So this can be, say, you can make kappa local, for example. Then you're still n squared, but at least you're bringing down the constant quite a bit because you only have to look at local neighborhoods. You can also assume that, say, kappa has some kind of fast decay, in which case you can compute multiple expansions. So if you look at the GraphCast architecture, which John also mentioned this morning, so the GraphCast architecture is precisely this with a multiple expansion on kappa. Okay? So you assume that the kernel, so you assume that the weather decorrelates at certain spatial scales, and then you try to compute this integral by hierarchically obtaining more and more points, or further and further points, the farther you are. Yeah? Another idea that also fits into this, here, the way I've generalized is that that's a linear integral transform. I can also make that nonlinear, and it turns out that has worked out very well as well, and that's called a transformer. So the self-attention mechanism is, again, this, but if you make your kernel integral kappa L depend on the input A. Okay? So now kappa is no longer just a function of spatial coordinates x and z. It's also a function of functions, which here is A. And then this function has this very particular kind of simple structure where you lift your input A into kind of a different space defined by these keys and queries, Q and L, and then you look at the similarity. So this looks at like how basically the further away things are, the less it weighs them, and it weighs them particularly by learnable elements, which are going to be Q and K. Okay, and then the normalization factor of this is there essentially, I would say, for computational reasons. So it's there so that inputs to the neural network, as they progress through the layers, roughly stay of the same scale. And this way, when you backpropagate, you get meaningful gradients. But really, the top part of that expression is what's meaningful and what actually makes this kind of the self-attention work. Of course, again, this is if you look at it in this way, this is quadratic in the runtime complexity. It will be 2n squared here because you have to compute the normalization and you have to compute the upper integral there. So that's 2n squared. So people have looked at all kinds of different ways of making this kind of computationally more scalable. You can, again, try to do patching, or you can do local attention. You can do localized window attention, or multi-grid type attention, which is the Swin transformer. There's kind of been a whole lot of works within computer vision. They have tried to make this faster, but it's really just this same idea, and all you can really do with any of them is kind of make this reduce the constant. So you're always going to be n squared with these kind of physical space methods, but you can try and reduce the constant quite a bit. And this does work. I do want to show that actually you can make this a bit more efficient. So here's an example. I just want to break up this presentation a little bit and show up one example of where we've looked at a few different transformer kind of architectures and compared it against an architecture which uses Fourier methods and the spectral truncation to do this. And you can see that in terms of the number of parameters, they do scale they can scale better. And in terms of the number of actual computational flops, these can scale well. But of course, this is only up to a point. Eventually, the n squared will dominate, and these will scale worse than, say, a spectral kind of architecture. But in terms of how well they actually work really well for capturing things that are maybe not so smooth. So here, the example on the left is a piecewise constant Darcy example, which was the first example that I showed you in this talk. And there you get, because the inputs have discontinuities, there are kind of surfaces within the solution where you're strictly H1 and no better. And so at those places in the solution, you really are not that smooth. And so you need an architecture that has a better inductive bias of not being smooth. Yeah? OK, so this is about 30 minutes in. So these are kind of all the example of architectures that I want to show you. I now want to talk about two instantiations of the curse of dimensionality. The first one will be the parametric curse of dimensionality. So everything that I say here will kind of apply to all the architectures that I've shown you so far. And we'll basically try to answer the question of how many parameters do we need in infinite dimensions in order to approximate well. Okay? So to get at that, first you need a notion of how big the set of functions that you're looking at actually is in the infinite dimensional space. Because I can take an infinite dimensional space, I can take a compact set K, which is, say, finite dimensional, and then from that, of course, I'm not going to hit the curse of dimensionality because I'm essentially doing finite dimensional approximation. So I have to first have a notion of what something really means to be infinite dimensional. Okay? And the notion that I'm going to use is this notion of alpha hypercubes, which is essentially a slight generalization of of looking at smoothness. So all these, so X here is allowed to be kind of any separable Banach space. And then I'm going to look at compact sets K, which contain alpha hypercubes. And an alpha hypercube is simply this kind of expansion where the lambda j's decay algebraically to some power alpha. Okay? So you can, the simplest example of this you can take is if you do Fourier series expansion, you can characterize HS spaces essentially precisely in this way, or you can at least embed them in this way. And you can also do this for Bezo spaces. You can do this for all kinds of spaces. This is just a general notion of how to think about size within an infinite dimensional space. And then it turns out that if I look at a set K, which contains such an alpha hypercube, then no matter what, there will always exist a smooth mapping, so a smooth G dagger, which is at least S time Frechet differentiable, for which the number of parameters that I need in order to approximate it to a tolerance epsilon scales exponentially. Okay? So this is a lower bound. So I'm saying that the number of, so in any of the architectures that I showed you before, the number of parameters which I need will scale exponentially. Okay? So this is, I would say, the kind of the parametric curse of dimensionality, because it tells you that essentially if you only think about smoothness, then you can never approximate it. So this doesn't tell me anything about any particulars of one problem. It just tells me that there will always exist a smooth operator for which I'll need an exponential number of parameters to approximate well. And if you parallel this to finite dimensions, where the curse of dimensionality is algebraic rates, in infinite dimensions, they become exponential. And this is what we saw also in the very first slide for the linear kind of architecture that I showed you. Okay. So a natural question you can ask from that is, if there will always exist these things where you need an exponential number of parameters to approximate, do there exist mappings for which you need an algebraic number of parameters? And the answer is yes. So to kind of get at that, what you do is you define what's called the approximation space of one particular architecture. So again, this is general, and this will work kind of for any of the architectures that I showed you before. So what you do is you define the space sigma m, which says that what if I look at all the mappings for which I only have m parameters? Can I then find the things, all the G daggers, that I can approximate well only with this number of given parameters? Okay? And by approximate well, here I'm saying something which decays like m to the minus gamma in the number of parameters. And this is natural because I just showed you that the curse of dimensionality in this infinite dimensional setting is exponential. And so efficient approximation means you're algebraic, while in finite dimensions, the curse of dimensionality is algebraic, right? So you have to kind of keep that in mind. Okay, so the answer to this, does anything actually exist in this space, is yes, at least. So this set, the set of things that I can approximate at a rate of m to the minus gamma is at least non-empty. But that's roughly the whole characterization that I can give you and that is currently known. And so this is slide. So I can show you here one particular example. If I take the Navier-Stokes or Euler equations and I set them up in a particular way where all the initial conditions are nice and smooth and all solutions tend to remain uniformly bounded in time, then the operator of taking such an initial condition and approximating the solution at a particular time, fixed time step t, does live in this approximation space. And you can characterize for a particular architecture here the number of parameters you need with this algebraic rate. Okay? And you can do this essentially by studying what happens in some finite element methods. So you can look at some spectral approximations to this problem, and then you can try and mimic that spectral approximation through a neural network, and you can get at a rate that looks like this. And people have done this for kind of a whole lot of problems. Gita Kitaniuk and collaborators, Sid Mishra and collaborators have looked at this for elliptic and parabolic type PDEs. Schwab and other collaborators have looked at it for holomorphic type PDEs. And then there's this notion of the Barron space, which kind of generalizes this, but makes it in a way so that things are not really checkable. But in any case, I don't want to focus on that. So the idea is that, yes, the space is non-empty. And the way we can prove that it is non-empty is essentially by looking at kind of what's already known within numerical methods. But apart from that, I would say that there really haven't been any new ideas in terms of how do you characterize these spaces. What is a good way of really determining that something lives in a space like this? And I would say that's probably one of the bigger open questions in this field. Okay, so you can approximate. So parametric cursive dimensionality is exponential, but you can approximate at algebraic rates certain operators, but you have to prove for every particular operator that you care about that you can do that, okay? Which is non-trivial. Another thing that we can look at is what about data? So how much data do I actually need to approximate efficiently? And we're going to kind of run into the same thing. So the way I'll look at data is through what's called the nonlinear n-width. So the notion of the Kolmogorov n-width is for linear method of approximation. I'll look at a generalization of this for nonlinear methods. So let me maybe go through the details of this slowly. So I will look at now a space X, which will either be continuous functionals, or will be a space of LP integrable functionals over some measure mu. So here, I'm making things a little bit simpler by looking only at functionals. So before, I had something that eats in a function, outputs a function. Here, I'm just taking something which eats in a function and outputs a number. Okay, so only functionals. And then within these functionals, I'm going to look at a particular nonlinear manifold, which will be the unit ball of all things which are S times Fauché differentiable. Okay, so the unit ball of all things that are S times Fauché differentiable, and then I'll define encoders, so something which maps me from this space X into n numbers, and then something which takes these n numbers and brings them back out into the space that I want to approximate in. Okay, and for that, I want to look at something worst case. So I want to look at what is the worst case over everything in my nonlinear manifold M of the best encoder and decoder, and try to characterize how this decays. Okay, and a particular example of this is something called the n-width, and the sampling width. And the sampling width is essentially when I take my encoder En and I make that a pointwise evaluation. So the encoder, the way I gather information about these functionals is I take in functions, I plug them in, and I see the number that comes out. Okay, and then from those numbers, I try to reconstruct. So I try to find the best possible decoder of the worst possible thing in SM. Okay, I hope that's maybe relatively clear. Okay, so for this, what you can prove is the following theorem above, which says that for any compact set K, which contains an alpha hypercube, so again, I'm using the alpha hypercube idea as a measure of kind of infinite dimensionalness, you can show that you have logarithmic lower bounds. Okay, so again, this tells you that you will need an exponential number of data points in order to approximate well in this space. Okay, so again, you have algebraic rates from finite dimensions translated into exponential rates in infinite dimensions. Okay, and then I can circle back and ask, can I again fix this? So for the whole space, so if I look kind of at the worst case of smooth things, this tells me that I'll always need an exponential amount of data. But certainly from practice, we know that this is kind of not true. And so it turns out that, yes, you can fix this. And this is this particular theorem. So this tells you that if you can approximate efficiently in terms of parameters, you can approximate efficiently in terms of data. So in particular, if I know that my target lives in the approximation space of the class of operators that I'm looking at, then I can show that kind of the worst case over this approximation class, so within the unit balls of this approximation class, then I get an upper bound which looks like the Monte Carlo rate, essentially. In the limit of smoothness, you recover back the Monte Carlo rate. And this is roughly the best you can ever hope for. Okay, so if you can approximate well in terms of parameters, you can approximate well in terms of data. In general, there is no hope. So in general, there will always exist kind of really, really bad maps for which you will need both an exponential number of parameters and an exponential amount of data. But I think, for problems that we care about, like the Navier-Stokes equation, this is not the case. We can, in fact, approximate efficiently. Okay, so I have so hopefully that gives a little bit of hope. I don't have all that much time. So the last thing I want to show, I'll just show you maybe just, yeah, I'll just show you one example. Yeah, I'll just show you this example because this is a dynamical systems conference. So I'll just show you a weather forecasting example. So here, what I'm going to look at, so I want to model the weather. And the way I'll do it is I'll think of the solution operator as kind of a non-autonomous dynamical system, which takes an initial state, which is some vector field that lives on the sphere and has k components, and then outputs another vector field that lives on the sphere and has k components. And the way I'll model this solution operator is precisely through the kind of parameterization that I showed you before, where T is now a spherical harmonic transform. So T takes your input, decomposes into spherical harmonic modes, multiplies by something that is already directly in the spherical harmonic space, and then takes an inverse through a spherical harmonic transform. Yeah. So this is roughly fast. It's not n log n. It's like n to the 3 over 2 n log n, which is still better than n squared, I'll say. And the way that we generally do this is because we have some observational data. We define things so that the next state approximation is going to just be a composition of your model with its own output. Yeah, and this way we can just, so it's just an autoregressive step where you can just keep composing with what comes out, and you can kind of try to predict trajectories. Okay, and what this is trained on reanalysis data from ECMWF. It's called ERA 5. Many people here maybe are familiar with that. We train it on 6-hour intervals, even though the data is available at 1-hour intervals, and we train it on roughly 40 years worth of data. So this uses an equiangular grid of about 721 by 1440 points on the entirety of the globe. And so when you do this, if you train for a very long time, what you can get is a model that is roughly competitive with IFS, which is the model that ECMWF has developed, which is purely a physics model. And this is purely a machine learning model. So we have used absolutely no physics whatsoever. We've simply taken ERA 5, constructed an operator of the kind that I've showed you, and trained it to predict the next step. And that's it, nothing else. And what I'm showing you here is basically a comparison against IFS on a few of the different kind of physical variables that one might care about. And you can see that it stays roughly, this is an integrated metric, where 1 is best. And so as you kind of predict forward, of course, things get worse and worse, but this is a chaotic system, so this is precisely what you expect to happen. But what this buys you is that you can actually inference this model much, much more quickly than the IFS model, because the IFS model is an actual PDE model that you have to solve. This is just a machine learning model that I can have on my laptop and actually execute once it's trained. So the training does take time, but once it's trained, you can put it on your laptop, you can execute it, and it's fast, and you can get probabilistic predictions by doing the same type of initial condition perturbation methods that IFS uses within their method. You can also apply them here, and you can get ensemble forecasts really at a fraction of a second than you couldn't do before. So I think that's quite a nice numerical kind of gain. Okay, so that's kind of all I want to say. I think I'm pretty much very out of time. So thank you very much.
So are there questions for Nick? Yes, Omar. I'll bring you the.
So yeah, Nick, I mean, just because it might have gone by fast and
Yeah.
the audience didn't catch it, when you say that the just hold it. All right. So when you say that the weather forecasting is purely machine learning model, there's no physics. I mean, it's trained on the reanalysis data, which is a data simulation with the full physics.
For sure.
So it uses all that information.
It does.
Blind.
For sure.
Yeah.
No, I agree with you.
Okay.
And I do agree with you. It just what I mean is that there's no physics in any of the machine learning parts. So there's no physics in the way that we design the model, or there's no physics in the way that we do the losses, there's no physics there. But yes, in the data, there's physics, absolutely, I agree with you. But this can be really said of any problem, right?
Yeah.
Like any problem where you do a simulation, and then you try and emulate it in some way, there is physics, but it's only in the data. Yeah.
And the second thing is, so that Navier-Stokes example, you said, there's hope and algebraic rates. The constant must depend on the Reynolds number, right? I mean, as the Reynolds number goes up.
Of course.
Yeah.
Yeah, so
I couldn't see from.
yeah. I mean, I've hidden all the constants.
Oh, you've hidden the constants.
Of
yeah.
course, because there's a tilde for all the constants, so all the constants live inside of here.
I see.
And yes, the constant depends, it depends on mu, so it depends on the viscosity. And of course, also it depends on capital T, which is the final time to which you approximate to. And yeah, I mean, that's all it should depend on here. And the domain, of course.
Okay, so the increasingly hyperbolic or advection-dominated characteristics
Yes.
are going to make life harder.
They absolutely are going to make life harder, but so the limit with mu actually does hold. So the constant does not blow up as you take mu to 0. So this does work for Euler as well. So that's kind of nice, at least.
Okay.
Yeah.
Thank you.
Yeah.
Thank you. Great talk, thanks. Regarding the ensemble forecast, you went through that fast. So how was the ensemble created? How was the different members created?
Different. So it is just through initial condition perturbations.
Initial condition perturbation.
Yeah, this is all initial condition
And
perturbations.
that's from ECMWF ensemble, initial condition
Yes,
perturbation?
in exactly the same way as they do it. Yes, yes. We are working on other. I mean, there's a lot of work now with doing things purely probabilistic without having to do initial condition ensemble perturbation. So this is through probabilistic models, but this is kind of current work that I'm not mentioning. Yeah, yeah.
Sorry. In the finite dimensional case, when you inform your neural networks of physics, for example, you can often get away with using less parameters. Can you say something similar about the infinite dimensional case?
So I'm not aware of any theory that says you can't do. I would hope that is true. That if you use, if you actually incorporate physics into a finite dimensional system, then you should be able to get away with a system that has less parameters. Although, as far as I know, that has not really been quantified. But I could be wrong. Maybe you know of a place where it is quantified.
No, I think it's just been more at least I've just seen it being
Yeah.
empirically observed.
Yeah.
Maybe in when there's these two paradigms of soft constraining models and hard constraining models. Obviously, when you hard constrain a model, you reduce the search space
Yes.
by a lot, and maybe there's some theory there. But I think, from what I've seen, it's been mostly empirical.
Empirical, yeah. So I would very much like to have some theory behind that, even in the finite dimensional case. So certainly nothing that I know of in the infinite dimensional case. But I think a good start would be the finite dimensional case. Yeah.
Are there other questions for Nick? I have one. Given an infinite computer,
Okay.
yeah, sounds pretty nice. Would you be able to train a foundational model on physics using this method?
Yeah, I don't know. There's been, I think there's a lot of claims recently that say things like this. I mean, given this theory, my answer is immediately no, because given this theory tells you that if you look across all kind of things, all kind of operators which are smooth, you run into the curse of dimensionality. And so if I want something which kind of works on everything, then the answer should of course be no, because you will always learn into the curse of dimensionality. I think for subsets of that, then maybe, yes. I think maybe if you just look at some particular types of fluid problems, then you can get something to extrapolate maybe between different viscosities. That sounds reasonable. But if you ask me, can I do all of physics in one model? I would certainly say no.
Okay. So are there other questions for Nick? Okay, thank you.
Okay,
Nick.
thank you.
Yeah. So now we have planned a coffee break, which if that math was difficult for you.